So I was saying that to formulate this, one way to proceed is to choose what are going to be my centroids, number one, and then the assignment of points to centroids. So one way of doing that is the following. We are going to use yj. I guess this is bad notation. Let me use a different letter. Let me use wj. So wi, this is going to be 1 if we choose xi as a centroid, and 0 otherwise. Okay, so that's going to be my wi. And then zji, this is going to be 1 if xj, okay, if xj is in the centroid, in the cluster with centroid xi and 0 otherwise. So if you make that choice of, so you can model your problem with that choice of variables, and it turns out to be the following. At the end, you end up minimizing the sum over I equal to 1 to n, j equal 1 to n of dij z. I guess if I want to be consistent here, ji. And then we have something that is very similar to what we saw with the facility location. The zji has to be less than or equal to wi. What this means is that I can only assign point j to the cluster that has centroid xi if I have already labeled xi as a centroid. Okay, so that's that. So this is for j, for I and j equal 1 to n. And then I need to pick k centroids. So these guys should add up to k. Okay, and both the wi's are binary, and the zi, ji, or ij, they also have to be binary. Okay, so this is for I 1 to n, and this is for j and I 1 to n. Okay, so this takes, a little bit of thinking, but even though at first sight this is not evidently an integer programming problem, after a little bit of thinking you can formulate it as an integer programming problem. So that's k-means and k-medioids. Another problem that I'll discuss in much more detail next time, because I find this to be a really, really very exciting, very recent development, is the best subset selection problem. This is an old problem that, of course, statisticians have known about and have thought about for many, many, many years. In fact, this problem is very directly related to the lasso model, right? So here, the problem is we want to find a set of predictors, right, for a least squares that, in principle, minimizes my least squares, and that the set of predictors has a size at most k. So here, for a change, of course, the x and y are data, right? X are a set of observations, and y is the response vector. And the variable, my function problem here is to minimize over beta, where we are including this constraint. So the objective is a nice quadratic objective. But we have this constraint that the 0 norm of beta has to be at most k. Okay? So the 0 norm just counts the number of non-zeros in beta. So again, let me give you the IP formulation for best subset selection. So this just relies on one small I guess, trick, and it's the following. So naturally, what makes this problem difficult is this constraint, right? I need to count the number of non-zeros in beta, the number of non-zeros in beta. So that is a very difficult constraint. That is a very non-convex constraint. So how do we formulate that? So the objective for this problem is going to be exactly the same. We are going to minimize over beta y minus x beta square. And we need to get a handle on this, right? So one way of doing that is to impose this kind of constraint. We want each component, we are going to use a whole set of new variables, binary variables, whose entire purpose is to help us count the number of non-zeros. So beta, I guess in absolute value, beta I will be bounded by some binary variable zi. So here the zi's are going to be 0 and 1 for I 1 up to p. So I need p new binary variables. My optimization problem here is going to be over beta and z. Okay? Now, this almost works, meaning the zi's essentially are going to flag what entries are 0 and what entries are not 0. When zi is 0, this will force me not to use that component, right? But when zi is 1, then I should be able to use this beta I. So if I just wrote this constraint, there is a little bit of a wrinkle there, because the beta I, when it's allowed to be non-zero, it could in principle take a big value. So the way to handle this is to put some kind of big M bound here, where M is an a priori bound on the entries of beta. Okay? And I guess I need one more constraint here to get a formulation, and that is I still need to restrict the number of non-zeros in my vector to be bounded by k. Right? And how do I count the non-zeros? Well, I just add the zi's. So the sum, I should have maybe written that earlier here. So the sum of the zi's, that should be less than or equal to k. Okay? And here, M is some bound, some a priori bound on the entries of beta. Okay? For example, if you just looked at the whole matrix X and Y, and looked at something like the norm of X transpose X inverse, then that would give you a bound. There are much more clever ways of getting a bound on beta. Okay? And again, that's something that I'll describe in a little bit more detail next time. But right now, what I want to highlight is that by introducing a binary variable, as you can see, this problem essentially has the same format as the problem at the beginning of class. It is a mixed integer programming problem where we are using these binary variables to account for that difficult constraint. Okay. All right, so that's the best subset selection problem. Here's another problem that I actually, until a little bit, like maybe a year ago or 2 years ago, I didn't know anything about this. This is called the least median of squares regression. So again, let's think about the same setting as that of best subset or that of regression. You have some data in Rn, some predictors and some response variable. And given a vector of coefficients beta, we call R just the usual residual, y minus x beta. So least squares, right? This is like what you learned shortly after you learned to talk, right? You learned least squares estimation. Right? That corresponds to minimizing the sum of the squares of the residuals, right? Now, least absolute deviation is an alternative to least squares that has certain properties with regard to the behavior to outliers, and that is to, instead of adding the squares of the residuals, add the absolute values of the residuals, and then find the beta that minimizes that, right? Least absolute deviation. Yes, sir?
We are not specifically focusing on the linear case value.
On the
Linear integer programming.
oh.
Or, for example, the previous problem was an integer program, but not a.
Oh, that's correct. Yes. So, good point. And I'll say a little bit more about that. So, maybe I can say a word about that now, and I'll say more later. But traditionally, so meaning until about 5 to 10 years ago, the main focus of research in integer programming was linear integer programming. But in the last 5 to 10 years, nonlinear integer programming, in particular quadratic and convex integer programming, that has really taken off. So now we actually have pretty good technology that goes well beyond the linear integer programming context. And that is important. It's a good point, because obviously this is not a linear problem, okay? The previous ones that we discussed, even the one for the medioids, that was linear, right? Once you see the formulation here, it's all linear. So that's a very good point. This is quadratic, and yeah, we can handle that now. We probably could not handle that 10 years ago, but we are living in very, very interesting times. So, okay, so the least absolute deviation, as I said, is just an alternative to least squares. And then there is this least median of squares, that the goal here is not to minimize any kind of overall sum of the residuals, but to minimize the median of residuals, okay? And I think some of you probably know more about this than I do. This has certain very special statistical properties, this kind of estimator. But there is a big difference between this guy and those guys up there. So if you look at the objective in the least squares, and even in the least absolute deviation, the objective that we are trying to minimize in both of those cases is a nice convex function. The first one is especially nice, right? It's a nice, smooth convex function. The second one is not quite smooth, but still manageable via linear programming. So the second one is still a decent one. By contrast, this problem is a much more difficult problem. This cannot be modeled as a convex, at least not as a manageable convex optimization problem. So now, if the lecture is going too slow and you are up for a challenge, think about how you would formulate this problem as an integer programming model, okay? The formulation is not that straightforward. And again, we'll discuss this next time. But this problem can be formulated as a mixed integer program, okay? And again, details coming up next time. So let me say a few words about how hard is integer programming. So it turns out that solving integer programs is very hard, okay? This is enormously hard. This is essentially as hard as a computational problem can be. So integer programming is NP hard. If you think about combinatorial optimization, right, there are all sorts of famous combinatorial optimization problems, like the traveling salesman problem, satisfiability problems. There are many, there's a whole collection of difficult NP hard combinatorial problems. Most of them have integer programming formulations. So the corollary is that integer programming is at least as difficult to solve as any of those NP hard problems. So in particular, the corollary of that is that we don't know, and we likely are never going to know, an algorithm that can solve integer programming efficiently. Okay, so that's bad news. But as Sometimes I hear colleagues talk in conferences. Some colleagues say, I only work on NP-hard problems. Okay? Those are the interesting problems to work on. So, you can look at this at the flip side. Because they are NP-hard, they really pose a very, very, very nice challenge, right? If you can crack one of those, at least with in some particular cases, then you make a good contribution. So now, there is a strong connection between integer and convex optimization. It turns out that, and I will discuss this in more detail in the next few slides, but often, let me put back the general formulation of a mixed integer program, how we are discussing it today, is basically is a convex optimization problem plus these constraints. Okay? So if we ignore these constraints, that is called the convex relaxation of the problem. Okay? If we relax those constraints, that's called the convex relaxation. If we relax those constraints, essentially we are letting the feasible set get bigger, so we'll get lower bounds on our problem. Okay? Typically we get a lower bound, and the lower bound provides some information about the problem, but we still may be some long ways from solving the problem. If we take the convex relaxation and then just naively attempt to round the answer, first of all, rounding may not be that straightforward. And second of all, even if we can round and produce an integer solution, the solution may be highly suboptimal. Okay? So those are kind of the kinds of difficulties that we face. So let me describe maybe the main idea that, or the main, how should I put it, like meta idea that goes into solving, that is applied to you to solve integer programs. And the idea at first sight is going to look like something deceptively simple, okay? Deceptively simple. But it turns out that this idea that I'm about to describe to you is enormously powerful. So suppose that I want to solve a problem like this, okay? So a difficult mixed integer programming problem. So there x accounts for all the constraints, okay? C and the integer constraints. So x includes everything. So this could be a fairly difficult set, x. Now, the first thing is that we don't know that there is nothing like KKT conditions or anything like that for integer programming. So even checking that a candidate solution is optimal, even just checking that is difficult. Okay, we do not have any kind of straightforward general optimality conditions. So suppose that someone comes to us and gives us x star and says, here, this is a solution. Think about the k-means and the heuristic that probably most of you know to attempt to solve the k-means clustering algorithm. You run it, okay, beginning with some random location for your centroids and adjusting them. And then the algorithm ends. How could you check that that is optimal? Okay. So again, there are no simple optimality conditions. But so here is a naive idea, an incredibly naive idea. Suppose that we can find a lower bound. Okay, suppose that we can find a lower bound and an upper bound. If those two guys are close to each other, okay, and they are, I guess I should have written here, so if they are close to each other, or if in the extreme, if they are the same, and they match the value of my feasible solution, then I conclude that that's a solution. Okay? Now, if I relax this a little bit, suppose I can get lower bound and upper bound, and they're close to each other. They're close to each other, and they sandwich a particular feasible value, then that feasible value has to be close to optimal. So let me actually write that down, because this is an incredibly simple but very powerful observation. So again, this is, say, a difficult minimization problem. Okay, suppose this is an upper bound, okay, and this guy is a lower bound, okay, and they also bracket the value of my current solution. Okay, so it immediately follows then that the value, I guess, I'm minimizing, so this guy has to be bigger. So this guy minus z, okay, this has to be bigger because I'm minimizing, and this is going to be smaller than z bar minus z bar. Okay, so if I can, this is kind of like a way of attacking the problem kind of from the side. Instead of trying to go directly for the optimal solution, if I can indirectly get bounds above and below, and somehow I can get those bounds to be close to each other, and somewhere in the middle I can squeeze a feasible solution, when those bounds are close to each other, I know that I'll be close to optimal. Okay, so that's the idea. As I said just a few minutes ago, this is almost the first time you hear this. It may seem deceptively simple. So let me pause here for a second, because what I'm going to do next is elaborate on this idea with a good number of bells and whistles. But this is the idea. This is how integer programs, for the most part, are solved. So are we all good with that? Question or yes?
But you only have the lower bound equal to the upper bound at the optimal, right? So
Oh, of course, yes.
Is it naive? Because, I mean, in the sense that to get that, you need to have the optimal. Like, how else is it useful?
Well, that I'll go into the details in a moment, okay? But at least you can at least appreciate that if you have upper and lower bounds that are close to each other, then at least this is going to get me near optimal, okay? So, all right. So let me. I guess that's what I have here. A template. A template essentially is going to go as follows. A template, and this template is very much the way that many solvers successfully solve very, very difficult integer programming models, is you iteratively generate upper bounds and lower bounds in such a way that as you generate them, you learn something about your problem and you sharpen them. And then you stop when you have a certain tolerance. And I guess, I'm not saying it here, but throughout, typically, the upper bounds are associated to a feasible solution. So once you have this sufficiently small, then you're happy that you have essentially found a solution. So that is the algorithmic template. Let me actually keep that template here. Yeah, here. So the bounds, okay, it's very standard to have this kind of terminology, to use this kind of terminology. So if you look at some of the literature, if we are minimizing, right, if we are minimizing, then primal bounds correspond typically to upper bounds. Primal bounds typically are associated to feasible solutions. So if you have any feasible point, that is, if you have a point in big X, naturally that is an upper bound on your problem, because your problem is a minimization problem, right? So any feasible point is an upper bound. Now, in some cases, in some problems, it is easy to find an upper bound. For example, think about the best subset selection problem. If you just arbitrarily select the first k predictors and then solve the least squares, that will give you an upper bound. Okay, so that is an easy case. By contrast, if you think about the knapsack problem, in the knapsack problem, it's not as obvious how you can get a good feasible point. So those are primal bounds because, again, essentially they are derived from the primal problem. And depending on the particular problem that you're working with, it may be easy or hard to find a feasible solution. Now, dual bounds, the name will become clear hopefully in a moment, but dual bounds typically are obtained from relaxations. So dual bounds, they will be typically obtained by solving a problem that is easier to solve than the original problem. But then, because we are tweaking the original problem, we are only finding a bound. And the name relaxation comes from the fact that they are guaranteed to give us I guess, a lower bound. Okay? A lower bound. So let me tell you what a relaxation is. I remember when shortly after I came to work here at Carnegie Mellon, there was someone who came to give a talk in our operations research seminar. And the title of his talk was The Art of Relaxation. And then he said that he was given a very hard time when he submitted a proposal to NSF with that kind of title, or, The Art of Relaxation. They thought he was out of his mind. Like, how dare he ask money for money for that? So, but relaxation has a very, very special meaning in optimization. So let me tell you what relaxation means in the optimization context, okay? So this is the problem that we generally are concerned with. So what is a relaxation of that problem? A relaxation is a different problem with the following two important characteristics. Number one, the constraint set of the relaxed problem is bigger. Okay, so every feasible point for the original problem has to be included in the relaxed problem. Okay, so the constraint set is relaxed in that regard. It's less constrained. But in addition to that, the objective function need not be identical. The objective function could be identical. That would be a relaxation. But in some cases, it's convenient to have an easier objective function. So we call the first problem a relaxation as long as we have this inequality for every feasible point for the original. Okay? So now, if you think about that for a moment, the two conditions, it immediately follows that if you solve the relaxation, you get a bound on the original problem, right? Because the relaxation, because of this condition, right? Because of this condition, the relaxation has an optimal value that is less than or equal than what it would be if I replace G with F. And because of the first condition, that in turn is also less than or equal to what would happen if I replaced, I guess maybe write it down here just to be clear. So observe if we have this problem, right? Mean G of X, X in Y is a relaxation of mean F of X, X in X, then, well, the first one, right? X in Y, G of X, this is less than or equal to, I guess I should be careful with the order here. So good thing I'm writing it. First, replace Y with X. So this is G of X, right? And this happens because Y is included in X. So this is G. And then this guy is less than or equal to mean X in X, F of X. Okay, and this is because G of X less than or equal to F of X, I guess. That. Okay, so the relaxation naturally gives me a lower bound. Okay. Now, the most common relaxation, maybe the most straightforward, is the convex relaxation. So we just lose the integrality constraints. So if that is my formulation, and F and C are convex, then this is my relaxation. Okay. So in particular, here is an example. If we look at the knapsack, we have max Cx, Ax less than or equal to B, Xj 0, 1. The relaxation, in this case, is max, right? So the relaxation is going to be the opposite. It's not going to be an upper bound, because, instead of minimizing, I'm maximizing. So the relaxation, this is important because we know that these are binary, right? Because we know that those are binary. When we have binary variables, the relaxation is always, by convention, we include the constraints 0 and 1. Okay, so the relaxation is the following. Max Cx, Ax less than or equal to B, x between 0 and 1. Okay? And this is called the linear programming relaxation, because it's a linear program. Okay? So that's the relaxation of the knapsack. Okay? And as you can see, this is a very easy linear program, right? It's only one constraint. It's a fairly easy one. Let me mention this business of Lagrangian relaxations, because convex relaxations are very straightforward. Okay? It's kind of the first thing that comes to mind. But it turns out that Lagrangian relaxations, this is a somewhat creative way of getting relaxations that sometimes turn out to be very powerful. So for instance, a case in point, if you browse the latest issues of, say, Operations Research, the flagship journal in Operations Research, that's the name, Operations Research, it is easy to see in any kind of random issue several articles that have to do with some Lagrangian relaxation approach to solving some difficult industry-related problem. Okay, Lagrangian relaxation is a way of getting relaxations for difficult integer programming problems that are much more informative, are far more informative in many cases than the convex relaxation. So what is the idea of a Lagrangian relaxation? And I want to spend a little bit of time with this, because if you want to take away one technical idea of today's class, I would let this be it. Okay? This is a really nice and very powerful technique. So suppose that we are looking at a problem of that form. We have some inequality constraints there, some linear inequality constraints, and some other bunch of constraints that could be difficult. Okay? So the x constraints could be very difficult constraints. They could include binary variables and all that jazz. Okay? Now, it may be the case that what makes the problem difficult is the combination of the inequality constraints and the other constraints. Okay, so in some cases, if we could break down and eliminate the continuous constraints, okay, the inequality constraints, this is a little counterintuitive, but in some cases, it may be the case that over x we can manage. So this is a very clever idea, and it relies on the Lagrangian function. It's very much in the same. It's an extension of the Lagrangian duality machinery that we discussed months ago. So we construct this so-called Lagrangian relaxation. We move the inequality constraints into the objective. So we shift them from the constraints to the objective via some multipliers here. Because they are inequalities, u should be greater than or equal to 0. Now, let me put back the definition of relaxation, because I guess, where do I have it? Here. Let me put back the definition of relaxation, because this is important. What is a relaxation by definition? By definition, a relaxation is one where the constraint is smaller and the objective function in the original constraint set is also smaller. So look at this. This is cool. If you look at this constraint set, this clearly is, oh, sorry, the relaxation has to have a bigger constraint set. Okay? So y has to be bigger. Now, we eliminated from the constraints, we eliminated the inequality. So clearly this problem has a bigger constraint set. So that first condition checks out. Now, what about this second condition? This takes a little bit of care, but it also checks out. If you look at the objective, it's not the same as the original objective, right? Because it contains this extra term. But if you look at the original objective at a feasible point, then at a feasible point, this difference is negative. If we multiply by some non-negative multipliers here, then this whole quantity is less than or equal to 0. So the second condition of relaxation also checks out. So this is a relaxation. And for any u, if we solve this problem, then we get a bound on the original problem. And now, if we want to find the best bound, we can do it by solving this problem. Okay. Now, there is something very, very neat that happens here that kind of is in a similar spirit to Lagrangean duality in convex optimization. This problem, this function, L of u, as a function of u, is a, I guess I'm minimizing here. So I claim that this is a concave function. This is a concave function. And because it's a concave function, then in principle, we can solve this problem via, convex optimization tools, what we have learned in the last 3 to 4 months, right? We can apply that to finding the best Lagrangian relaxation, okay? So I know that we are used to a quick break. So here is something. Think about why this is concave. And I'm going to give you an example of Lagrangian relaxation that works extremely well. But in the interest of having your full undivided attention, I think that this is probably a good point for a very short break. So let's just take about 4 minutes, stretch, get some water if you need to, and think about why this is concave. Okay? So let's resume. So before we resume, right, don't forget those peer reviews, right, by Wednesday. Don't forget to do that. OK, so why is this guy concave?
You transpose times something that's negative. So the negative of that is like an affine, is like you transpose times something that's positive, and that's convex. So the negative of convex is concave.
Yes, actually, that is correct. But it's actually even simpler than that, right? Because if you think about this guy here, right, this component is actually not only the negative of a convex function, but it's actually an affine function of u. Right? This is a linear function of u. So all we are doing here is taking the mean of a bunch of affine functions. Okay? Remember that the sup, or the max, of a bunch of convex function is convex. Here, this is the mean of a bunch of linear functions, which are concave, as you pointed out, because they're linear. Naturally, that is concave. Okay? So this is by construction. L by construction is a concave function. So maximizing it, in principle, is amenable to techniques for convex minimization. In this case, it's concave maximization. All right, so let me give you an example that I think is really cool, because the facility location problem that I mentioned earlier, facility location here. So facility location is a very difficult problem. This is a notoriously difficult problem. I mentioned earlier that we teach business school students, we teach them integer programming because this kind of stuff comes up often in various types of problems in logistics and in production and healthcare and many other areas. But this is a very difficult problem. Okay? Computationally is very difficult. So there is a neat Lagrangian relaxation for this problem. The Lagrangian relaxation is a very clever one because it is a bit, and it's a little counterintuitive. The constraint that we are going to move out of here is the constraint, this constraint, this guy, this set of constraints. Those are the ones that we're going to move to the objective. And we are going to purposely leave all of the other constraints, the discrete ones we're going to leave. Because once we move that guy to the objective, it turns out that this problem is actually easy to solve. So here, the difference between this and that is that we took the first constraint there, multiplied it by multipliers v, and added to the objective. In this case, because this is the constraints are equality constraints, then the v's need not be, they are not restricted, they are unrestricted. And it turns out that the Lagrangian relaxation is easily solvable. I'm a little tight in time, so I'm going to skip the details, but just take my word for it. Computing the solution to the linear relaxation is very easy. To the Lagrangian relaxation, sorry, is very easy. Even though the Lagrangian relaxation itself is, the Lagrangian relaxation is actually a combinatorial problem. Still, solving it turns out to be easy. Okay, so you can solve that, and also, in addition, we can get a subdifferential, an expression for the subdifferential for the negative of the Lagrangian. So finding the best relaxation it can be done, for example, via a subgradient method or something of that sort. So that's an example of a Lagrangian relaxation. The last I want today about is, so Lagrangian relaxation, is a way of obtaining relaxations, but I want to conclude today with a general algorithm for solving integer programs. And in fact, this algorithm is kind of this idea, this template, is what is used by most commercial solvers for integer optimization. It's the so-called branch and bound algorithm. And the idea of branch and bound is basically a kind of divide and conquer approach. Divide and conquer approach is the idea of break the original problem into smaller, maybe more manageable subproblems. So for example, suppose that we want to solve this problem, minimize f of x in big X. So for instance, suppose that some of the constraints are binary constraints. Binary constraints. So you can naturally split the feasible set according to the binary constraints. So for example, if your first variable is restricted to be 0 and 1, there is a subproblem where that first variable is frozen at 0, and another problem where that is frozen at 1. Okay? You can even take that a little bit further. If you have 5 variables that are binary, you can generate 2 to the 5 subproblems and then solve them separately and then look at the best one. That is the idea of branching. Okay? Now, at the extreme, if you had binary variables, okay, if you had, say, j binary variables, then you can branch into 2 to the j subproblems for all the possible choices of your binary variables, and then choose the best one. But of course, that would not work if the problem is large. So the idea of branch and bound is that you branch, but you keep things, you don't branch too much. You branch it only with a few branches at each step. So, so here's the deal. If we branch the problem, if we partition the domain of the original problem, and we solve each one of the subproblems, right? If we actually solve them, then we just have to take the best one. Now, suppose that we don't necessarily solve all of them, but if we get a feasible solution to any of them, that would also be a feasible solution to the original problem, and therefore we get an upper bound. Okay, we get an upper bound. Now, here is the key idea of branch and bound. For each problem, we could use a relaxation to get a lower bound on that subproblem. Okay? We get a lower bound on each problem I. If that lower bound is bigger than the upper bound that we have so far, so think about the upper bound as a terminology that is frequently used in integer programming is the incumbent solution, right? That we at some point, we managed to get a feasible solution. That's our best solution so far. If that best solution is less than the lower bound subproblem, then we can discard that subproblem. We don't need to worry about that subproblem anymore, because this guy being a lower bound guarantees that that subproblem, the best that subproblem could be, is going to be bigger than that lower bound. If we already have another solution that is better, then we need not bother with this subproblem. This is a key idea of branch and bound, because that means that we don't just do some kind of brute force branching. This is branching, some smart branching. You branch, but then you keep track of some solution that you have found so far to prune your branching. At some point, you discard a lot of the branches that you would otherwise naively explore. So this is kind of a key idea. This is the key component of branch and bound. So this is the algorithm, essentially. If you want to solve that problem, the problem at the top, you can start by solving, say, the relaxation, the convex relaxation. If the convex relaxation is infeasible, then you immediately conclude that the original problem has to be infeasible because it has more constraints. So that's easy. Now, if you solve the convex relaxation, and you're lucky enough that the solution to the convex relaxation is also feasible for the original problem, that is, we ignored the integer constraints, but we are lucky enough that the solution we found is integer, then we're happy. That has to be an optimal solution to the original problem. Because it's already feasible, right? I guess, yeah. So in this case, this would be easy also. Now, if the solution to the convex relaxation is not feasible for the original problem, that means that there is a variable that was supposed to be integer in the original problem, and that when we solved here, did not come out integer. So we have two things to do. We get a lower bound, but we also have some kind of guide to branch. So we branch on that variable that is fractional. And we create two new problems. We branch and we solve the two new problems. Okay? And let me maybe highlight this point. So this is, again, a key component of branch and bound. So let me put this here. So this is the idea of branch and bound. It's essentially a recursive enumeration algorithm. When we branch, we will solve the subproblems, but we solve them cleverly. We don't just solve them kind of by brute force, but we solve them cleverly. First, we compute a lower bound, which typically is easier to compute than solving the entire problem. If the lower bound is larger than the best solution that we have found so far, meaning if the lower bound is larger than the current best upper bound, then there is no need to explore that subproblem anymore. So that's branch and bound. So I just have a couple of minutes. Let me kind of illustrate that with a picture. So here's how branch and bound will typically, so this is a typical branch and bound tree. So this is called the root node. This is the convex relaxation. Then we branch. So this is subproblem, say 1, subproblem 2, okay? And then in principle, we keep going recursively. So if we were naive, this would just keep going on forever, right? Branch again, and branch again, and keep branching. But at some point, we find, let's say we go down this way, this path, and we find here some feasible solution to the integer program, okay? So this gives us U. I guess that's what I called, where did I put it? Yes, I called U of x. So when we branch, we get U of x. If this problem here has, let's say, L is less than or equal to, if the lower bound here, sorry, the other way around, if this lower bound is greater than or equal to U of x, then all of this can be discarded. There is no need to explore all of this part of the branching, because from this point onward, if the lower bound of this subproblem is bigger than U of x, whatever solution I find here is going to be worse than this solution here. So I can discard all of that. So that is the basic idea of branch and bound. And that is how, with many more bells and whistles, we can solve integer programs. So there is a comment that I remember once having lunch with my colleagues, my senior colleagues in the Tepper School. They were asking, who is the main user of linear programming? Who are the main consumers of linear programming? And the answer of them was, integer programming are the main consumers of linear programming. To solve an integer program, you solve many, many, many convex relaxation problems. So the people who keep linear programming solvers particularly busy are those guys who are solving integer programs. Because during this branching, you need to keep solving many, many relaxations of the original problem. And that involves solving many, many convex relaxations. If the original problem is linear, then these are all linear programming relaxations. All right, so I think this is a good point to stop for today. Next time, I'll tell you more about algorithms, for a little bit more about algorithms. And then I'll tell you more about applications, in particular the best subset and the, what was the name again? I keep forgetting. Least mean, these two, least means of squares regression. Okay? So we'll do that on Wednesday. And again, don't forget your peer reviews.